What is something that can only grow larger but never shrink? Almost anything you can think of, whether it's plants and animals on Earth or planets in the universe, can be made smaller if you force it. But there is one thing that no amount of force in the universe can make smaller: the black hole. This ties into a law proposed by Stephen Hawking, the area theorem, which says the surface area of a black hole's event horizon never decreases. Whether a black hole consumes matter or two black holes collide, the final surface area will either grow or stay the same. It never gets smaller. Huh? You're saying Hawking radiation can make a black hole evaporate? That's a separate issue. We'll talk about it at the end of the video. The black hole area theorem comes from a new field that emerged in the 1970s, black hole thermodynamics. It even features 4 laws of black hole thermodynamics, which correspond to the 4 classical laws of thermodynamics. The 0th law of thermodynamics says that a system's temperature is uniform throughout when it's in thermal equilibrium. The 0th law of black hole thermodynamics says that for a stable black hole, the surface gravity is the same everywhere on its event horizon. It's uniform. In other words, if we don't factor in Hawking radiation, a black hole's temperature is just its surface gravity. Next is the first law of thermodynamics, which says energy cannot be created or destroyed, it only transforms from one form to another. During these transformations, the total amount of energy stays the same. This is what we call the conservation of energy. The first law of black hole thermodynamics says that when a black hole absorbs matter or energy, its mass, angular momentum, and surface area change accordingly. These changes are tightly constrained by equations, just like energy transformations in thermodynamics. In a sense, this is also a kind of conservation law. The second law of thermodynamics is even more well known. It says that the entropy of an isolated system never decreases. This is the law of increasing entropy. Hawking was inspired by this law and realized the surface area of a black hole also only goes up, never down, just like entropy. But the surface area of a black hole is inversely proportional to its temperature. That means as a black hole grows, its temperature drops, its surface gravity gets weaker. But no matter how low it gets, the temperature never reaches 0, and that brings us to the third law. The third law of thermodynamics says you can't reach absolute 0 in a finite number of steps. The black hole version says the surface gravity of a black hole can never be reduced to 0. This law rules out the existence of extreme black holes called naked singularities. It's these 4 laws that turn black holes, these exotic objects, into ordinary physical systems that obey thermodynamic rules. But here's the catch: if black holes have temperature, shouldn't they also emit thermal radiation? Traditionally, black holes are considered one-way traps. They only absorb, never release, so they shouldn't radiate energy. To solve this, Hawking later proposed his famous Hawking radiation theory. But that's another topic. Let's get back to the black hole's surface area for now. Since we're talking about black holes only getting larger, how do we actually calculate their area? Isn't a black hole just a sphere? Can't we just use the formula for the surface area of a sphere? Exactly. If we know a black hole's mass, we can use the Schwarzschild radius formula to find its radius, then plug that into the sphere's surface area formula to get the area of a non-rotating, uncharged Schwarzschild black hole. But in reality, most black holes aren't static. They're rotating curved black holes. When a black hole spins, it isn't a perfect sphere anymore. It's squashed into an ellipsoid, just like Earth bulges at the equator because of rotation. For these flattened, rotating black holes, you need to factor in a spin parameter based on the static black hole model. The faster the spin, the smaller the black hole's surface area. So, how do we actually test if this area law holds true? Scientists came up with a clever approach using gravitational waves. Gravitational waves are ripples in the fabric of space-time. When 2 black holes collide, the immense gravitational disturbance sends ripples through space-time. These are gravitational waves. By analyzing these signals, we can figure out the mass and spin of the black holes involved, and use that to calculate their surface areas. Just add up the areas of the 2 black holes before they merge, then calculate the area of the bigger black hole after the merger, and compare the two. On September 14, 2015, the LIGO Observatory detected gravitational waves from a black hole merger for the very first time. It was humanity's first direct observation of a black hole merger. After analyzing the data, scientists determined the waves came from 2 stellar black holes, one 36 times the Sun's mass and the other 29 times. Together, they formed a larger black hole, 62 times the Sun's mass. Now you might wonder, 36 plus 29 is 65, so where did the missing 3 solar masses go? In short, they were released as gravitational waves. But wait, aren't black holes supposed to only absorb and never release anything? How can their mass decrease? Here's where we need to clarify. When we talk about a black hole's mass, we're referring to both its gravitational mass and the equivalent mass from its rotational energy. The first part is called irreducible mass, the core mass of the black hole, which is what we mean when we say only absorbs, never releases. The latter refers to the mass contributed by the black hole's angular momentum, essentially the mass that's derived from converting energy according to the mass-energy equivalence. Add these two together, and you get the black hole's total mass. Gravitational waves don't release the first kind of mass, but rather the second, the mass that corresponds to the black hole's rotational energy. Back to the black hole's area, calculations show that the combined area of the two black holes before merging was about 235,000 square kilometers, while the area of the new black hole formed after the merger was around 367,000 square kilometers. It's obvious that the total area of the black hole has grown. This marks the first confirmation of Hawking's black hole area law. But the signal wasn't very clear. The signal-to-noise ratio was only 26. We could see the area increased, but the measurement wasn't very precise. Over the next decade, scientists kept upgrading LIGO to improve its sensitivity. Then, on January 14, 2025, LIGO detected an extremely clear gravitational wave signal with a signal-to-noise ratio reaching 80. This signal came from two black holes merging 1.3 billion light-years away, one with 33.6 times the mass of our Sun, the other with 32.2 times, and together they formed a new black hole 63 times the Sun's mass. The area of the new black hole was clearly much larger than the combined areas of the two smaller ones. The confidence level for this result surpassed 4 sigma, hitting 99.9999%. This was the most precise test of the black hole area law to date. This research not only confirmed Hawking's area law, but also provided a test of the black hole no-hair theorem. That theorem states that a black hole can be fully described by just 3 basic properties: mass, angular momentum, and charge. Of course, we can ignore charge for now, since it's generally believed that charged black holes don't exist in reality. Finally, let's revisit the question from the start. If Hawking radiation causes black holes to slowly evaporate, doesn't that contradict the area law, which says their area only grows? Actually, there's no real contradiction, because the area law comes from classical general relativity, while Hawking radiation is a quantum phenomenon. Even if a black hole does shrink due to Hawking radiation, the second law of thermodynamics still holds. That's because, although the black hole's area gets smaller, the entropy carried away by its radiation increases, so the total entropy still goes up. This is called the generalized second law. So, looking back on the whole story, from Hawking proposing the area law in 1971 to LIGO's first detection of gravitational waves in 2015 to this highly precise verification in 2025, there have been both technical breakthroughs and theoretical advances. Countless scientists have contributed to making this possible. As technology keeps improving, we believe even more and clearer signals will be discovered. Why is a black hole's area so similar to thermodynamic entropy? Are they fundamentally the same at a deeper level? Maybe future research will give us answers to these questions.